ways to do it, of course, but in Julia, there's sort of a lot of basically staging mechanisms that we ended up using to coerce things into gen models.
So just to summarize again, so you're taking, is it, I assume it's for like simulations, is it only, or things, or it's kind of a model that you would write of a simulation, and then
it can actually be anything. So, well, I say that. There's, of course, caveats that we haven't tested everything. But generically, it can be any program. But the transformation looks for particular calls, calls which can be reinterpreted in terms of tracing calls with distribution objects, which Gen knows how to handle. So you could pass in a program which doesn't have any randomness. It won't really do much. It would still convert to a generative function. But of course, you wouldn't have any trace statements in that.
Any good tutorials? No?
Let me think about that. I'll have to check the state of the repo, see where it's at.
It'd be cool to work through like an SIR model example for see if it's.
I think Shen was putting together a Jupyter Notebook tutorial for a presentation tomorrow. So I'll ask Shen and determine whether or not that sort of tutorial material ready.
Sorry, I didn't mean to like blow up your spot and put a lot of pressure on you.
No problem. Okay. That's all right.
Still waiting for folks to trickle in.
Hey, Zena, I saw you're presenting something on parametric inversion at Laffy. Looking forward to it, and congrats.
Yeah, thanks. You too.
Thanks.
Congrats. Also you, McCoy.
Yeah.
Say that one more time, sorry.
Just saying also congrats to you.
On Laffy.
Oh, yeah. Yeah. I'm super excited. I won't be able to have beignets this year, unfortunately.
Yeah, sadly, no. Yeah, the CogSci conference in July has already stated that they'll have an in-person component in Vienna, but I don't know if MIT's like travel ban will still be in effect.
Yeah, that's ambitious.
Yeah.
I'm trying to think. So I know ICML has said it's going to be virtual next year. I don't know about the like fall conferences. Have they announced? Does anyone know?
No, I don't think so.
Yeah.
It seems beneficial to have a virtual component just from like an environmental perspective. That's like one thing that I've been thinking about. I'm not sure if it's like a standard viewpoint, but it seems like it's a lot of carbon being saved.
I mean, you have to balance that against how much carbon would be saved by people forming world beneficial collaborations by meeting at these conferences.
Right.
Yeah, Popple is gonna save the world.
I don't know.
I mean, we're going to
prove global warming out of existence.
No, we're going to develop more efficient and more efficient languages and reduce the. I mean, right. I mean, seriously, like cloud computing contributes a significant fraction of emissions today. So everything you do, well, actually, I guess if make computers efficient also increase demand for compute. But outside the indirect effects, the direct effects of everything in performance is reducing global warming.
That's a generous interpretation, I think.
You can say that, but it's also, there's very literally true, direct line.
Yeah.
Yeah. That whole direct effects only thing is doing quite a bit of work, but yeah.
Good transition, Alex.
Yes, it has the word effects in it.
Yeah.
So Sammy, you recommended these TMLE papers. Do you?
Yeah.
Um,
Were
so-
there
so-
multiple?
there was one for next time as well.
Yeah, so I should mention the one for next time is a textbook. So I don't think we should read that one.
Oh,
Yeah, actually, if we were to continue in this version, or in this kind of thread where we have a doubly robust estimator that's efficient, that is uses substitution, so it's robust to sparse data and all these kinds of things, that the next method that I think we should look at is the one that actually came out of Johns Hopkins. It's Ilya Spitzer's and Rohit Bhattacharya and Rezi, I forget her last name. They just published the semi-parametric approach that works for any identifiable causal query. It doesn't have to be restricted to measured confounders. It can work for everything. So TMLE is great if you have a bunch of measured confounders, but if you have a bunch of unmeasured stuff, latent variables, you're out of luck. TMLE won't do well at all. But this will work for any of it. So the nice thing about the semi-parametric approach, it's not the most accessible paper, but they do a good job writing it. But there's a little bit of background that you need in semi-parametric theory, and there's a simple paper, like less than 8 pages, that kind of gives that background. And then they also have a 1-hour seminar that explains it, and they also have code that you can actually write. So all those methods, you can actually just, in Python, you can execute their different methods on different DAGs, and it all works.
Cool. Yeah, I'm certainly open to it. I don't want, I guess let's gauge the room to see if people like this semi-parametric inference stuff. I guess the reason I brought up this theme of papers in the first place is because it's not obvious to me how to translate these ideas of double robustness. Jeremy, I'm vaguely familiar with these like efficient influence function type semi-parametric theory methods, but it just feels like in this separate category of thing. But based on the small simulation study here and talking to other causal inference researchers, it seems to work pretty well. So yeah, I guess this paper was pretty short. I think it was meant to be an introduction mostly for epidemiologists. Not a lot of technical meat in it. But I don't know. Yeah, what did people think? When people read this paper, did you think like this is a silly thing to do because we never misspecify the outcome function, or?
Well, the purpose wasn't only to be robust to misspecification, right?
Right.
Like there's some argument that you get a better estimate after the second round of targeting.
Right.
So
Right.
my main reaction was that I really appreciated the exposition at the beginning and found that helpful for framing for someone who sort of has to be reintroduced to these ideas every paper that I read because I haven't systematically studied them. But also feeling like I didn't get why this crucial step 3 works, or like what exactly it's doing, right? Yeah, so that was my like first order reaction, and my second order reaction was I think it would be interesting to discuss with you all. I mean, just some of the ideas that we started discussing in this group of how do you take techniques that are being written about or applied by practitioners and think of them in light of the tools that we're creating. Like what kinds of tools would be necessary to apply techniques like this? How would we think about techniques like this? And the how would we think about techniques like this is harder for me to think about just because I haven't internalized why this third step works. It's mentioned that it's derived from the canonical gradient, but I don't know what that is referencing.
So a question I kind of, when I read papers like this, I don't really get excited about papers like this, which means that I'm only reading at about half attention anyway. So, but what I see is that, oh, okay, they're just finagling estimators to get a better bias variance trade-off, and which of course is very practical. And if I ever had a problem where I'm like, oh, my variance is exploding, how do I fix that? I'd go and read papers like this. But then but at that point it becomes a stats paper, and right, and that's fine. I just kind of think to myself like, am I? Yeah, I guess there's a clear line in my head between causal modeling and statistics. Like they sit in different regions of my brain, and so like these papers that mix the languages together, I just find them a little bit tedious. But am I missing something, or is that a?
Yeah, well, I think the thing that I like about TMLE is that if you are in if you're kind of Pearlian causal inference, Estimand causal inference engine world, and you actually have some real data in hand, how do you actually apply your DAGs to solve a causal question, to actually estimate it from data? And without TMLE, all sorts of bad things can happen, right? Suppose you misspecify the outcome distribution, or the outcome parameter, or suppose you misspecify the. So if you're going to do inverse probability weighting, then you try to estimate the probability of a given x, right? Where x is the covariance and a is your treatment, right? If you misspecify that, all bets are off. And likewise, if you use G computation and you misspecify the outcome, probability of expectation of y given a and x, if you misspecify that, all bets are off. In this case, if you misspecify either one of those, but you didn't misspecify the other one, then you're okay. And if you get them both specified correctly, then you end up with an efficient estimator. And furthermore, it uses a substitution estimator, which means that even if you have low data, low amounts of data, you still get it's still robust to like sparse data. So yes, I guess these are all statistical questions, but like it gives me and I think that's what was the intent of the TMLE paper, is like, you don't have to worry. Double robustness saves you from screwing things up. And so, and it's specifically for a causal question, right? So if you have an estimand, how do you estimate that estimand from data? And I guess this is a question maybe for Eli and Robert. You guys, kind of work with probabilistic programs, and so you just generate the joint distribution, and then marginalize or whatever you need to do, and you're done, right? You don't have to worry about estimating things from data. Or is this estimator like, kind of, do you guys not think about it in the same way as I need to create an estimator for a specific causal parameter because I have the joint distribution in hand, so I don't need to worry about anything else?
Well, I guess I'm sort of puzzled by, I don't understand. If you started with a joint distribution, it's a little unclear to me how, you'd be in a situation where one was correct and one was incorrect.
Right, exactly.
One of the two estimators was misspecified instead of both or none. I guess that's like, it seems like there's a bunch of stuff going on in this double robustness property.
Right. So you're never
this particular implication. I guess it's easy to see how a statistician writing down their potential outcomes might stumble onto something like this, but it's a little harder to see where it would come from if you started from a kind of a joint distribution.
Yeah, or if
people have some insights into the plausibility of this particular form of specification.
Is anybody familiar with M estimators? It's a class of estimators and statistics that I kept thinking about when I was reading this paper. But yeah, I suppose my answer to Jeremy is like, if from probabilistic programming standpoint, since the inference is typically Bayesian, I would be thinking, all right, how, if this is if this is some kind of doubly robust estimator and it works with sparse data, then there's some, in a Bayesian sense, there's some kind of prior that's being applied, and I'd be wanting to think about what is the prior and what is it being assigned to. But I didn't really muse too much in that direction.
So I think,
Robert,
part of this. Sorry, Alex, were you going to say something?
Go ahead.
I think part of this paper gets a little bit stuck in the craft of statistics, like you're saying, Robert, of, they're putting a lot of effort into this double robustness property. Sounds like as a group, we don't really care about it that much or believe that it's a viable, that this is likely to help us, but it's in the language of statistics papers. So to get your paper published, you need to show, double robustness in this kind of way. Kind of like how, the name of the game a long time ago was minimum variance unbiased estimators. And then we said, oh, a little bit of bias is fine if we can drive the variance down. So I think, right, a part of that, I agree, doesn't hold a lot of weight. But as I forget, someone mentioned at the beginning, it was either Jeremy or Alex, even if the true model is within your model class, right, your hypothesis space, you will get, lower error, right? It's not just about misspecification. It's about minimizing this error term. And that is something we should care about, even if we don't buy the premise of, double robustness.
Yeah, I'm interested in understanding the reason that this works and generalizations of it, right? Like, and maybe the generalizations of it piece could play a little bit more into causality in particular. Like, how do you think about these estimands and then estimation procedures in arbitrary causal models for arbitrary causal queries, if that even makes sense. But I don't have from a probabilistic programming perspective, I'm interested in the idea that you can have sort of like an estimate, but then because the particular parameter of interest, this ATE, like you're able to use that in some way to reduce the variance or something, or optimize the bias variance trade-off. But I don't have a good sense of how it's being used. So mostly that's like a very vague sense that I'm getting.
Yeah. It's like step one is measure the out or get an initial estimate for the outcome, and step two is to get the effect of the exposure. And then there's this kind of magic of step three where you improve your estimate of the ATE by somehow combining those two. And that's the part that wasn't clear.
And is it repeatable? Like, can you iterate this again and again and keep getting a better estimator until you converge at something? Or is it idempotent where you just, if you do it again, you get the same estimator?
That's an excellent question.
So they have this notion of super learners, which they say basically the plug-in part is that you can use any machine learning or just an ensemble of machine learning methods to get a better estimate for the ATE, and so maybe that's.
I mean, that makes sense to me that, right, these steps that are like estimate this quantity you could do with anything.
So I think behind the scenes in the 100-page targeted learning manifesto that Mark van der Laan wrote, the precursor to this, there are some conditions on the sort of class of estimators that you can use. So in part, I think super learner is marketing, right? It's like fancy machine learning, cool. But it's also an ensemble that has those particular properties. Yeah, I will also say, just as an extra sort of context point, if you look at the original targeted learning paper, it actually doesn't mention causal inference anywhere in the paper. It's just about, I have some random variables and I have some functional of those random variables, and I want to minimize the bias variance trade-off of that functional. It just happens that in causal inference, we're interested in the contrasts between, you know, counterfactual outcomes. So that's a functional of the random variables. It sort of fits the template.
Right. It's just
And I wonder,
you take the TMLE estimator and apply some causal assumptions,
right?
And it becomes a causal estimator.
Right.
I wonder if another point of interfacing with PPLs here is to Zena's work on random conditional distributions, because when you say a functional of random variables, you mean a function of the distributions of those random variables, right? That's what the ATE is.
Yeah, seems like it. Although I feel like I feel like my take on this paper was very similar to yours, Alex. Like I read through the steps, but didn't really understand why or like how they were connected. Like even step one, like I wasn't sure, like, are we, like, this is a conditional expectation. Like are we learning an estimate of a value or of a function of what A and X, or of an actual conditional expectation, right? So,
well, I think you should just read that as estimating a probability distribution of values of y given values of A and X.
right.
Just taking a regression model and fitting it to pairs of, y, x, A.
Right. Yeah. So that's what I thought, but that's slightly different to a conditional expectation.
It seems like they only use it as a mapping from AX to the conditional expectation of Y, right? So even if like it's a like learning, like if you had a method for getting that expectation, like, right, I guess you could use like supervised machine learning without uncertainty, right? Like just have a neural net that outputs Y and probably plug it in here.
I guess that's what they're talking about in the section 5 or whatever it is, the neural network section. But yeah, I didn't really get how these parts built on top of, like, I didn't get how you had this kind of boosting effect where you could just improve things through step 2 and step 3.
Right. This canonical gradient makes me think that there's some formulation of this as a gradient step, either as an optimization of the estimator. But I don't know.
I would assume that if you just wrote out an expression for the variance of ATE, then the fact that you've got these two unbiased estimators that you constructed in this way means that some of the variance terms will cancel out. And that's why it ends up being better than a one-step thing.
You're saying if you write out not the variance of the ATE, but the variance of their estimate of the ATE from, like, is that what you mean?
Well, they're combining these estimators in such a way, right? There's these sub-steps of estimating these individual quantities, the propensity scores and the
and then they have this HA thing and
potential outcomes, and the way they combine them is such that if you write out an expression for the variance of the ATE estimate in step 4, that some terms will some variance terms that are introduced by adding the individual estimators will cancel out. And so the whole thing is lower variance than if you just did the G computation thing and combine your two estimators of the two potential outcomes.
That makes sense as a way of proving or verifying that this procedure leads to a lower variance estimate, but I'm not sure that gets at how it was derived, or like sort of understandable like it's possible that they just wrote out some equations and noticed that you could do this, but they say that HA can be derived from the canonical gradient, which maybe I'm reading way too much into. Yeah.
I see what you're referring to. I don't know what that means in the context.
Yeah, no, me neither.
That literature. But I don't think it's a particularly deep insight. Like I think there's a cottage industry of little recipes for combining regression models to produce treatment effect estimating. Targeted learning is one.
Do you not think
there's these other popular ones called like X learners and R learners and T learners?
Yes.
They all mix estimators for propensity scores and potential outcomes in different ways.
And do you think there's no sort of, I mean, I guess, what role does, one of the things that I like about programming languages research is that there's an emphasis on finding like underlying patterns of compositionality behind like huge areas of computation, like huge sets of computations. And I think there must be principles that I don't know much about because I haven't thought too much about like manipulating the variance of estimators that could be thought about in a more unified way, probably. And that, there could be tooling that we could provide, like both conceptual tooling and then actual automation that would help in the like construction of these things. But that's just a hunch. Like I think going through some of these proofs would probably help.
I mean, in terms of where do we kind of look for optimal properties of estimators in Bayesian statistics? You can look to Stan, where so for example, Andrew Gelman and Michael Benencourt have a bunch of papers on what are the kinds of priors that you use to get to certain properties under certain circumstances. So I mean, like in that setting, it's all about picking the right prior for the right problem for the right parameter.
Are you thinking of like non-centered parameterizations and centered parameterization?
And yeah, or even simpler things like, for example, like if I want to put a prior on a scale parameter, should I use a gamma distribution or should I use a half Cauchy or something like that? And there's a bunch of guidelines on how to do that, but I don't really know how you make that user-friendly. You just kind of have to read statistics papers.
Yeah, I guess I'm not as pessimistic about this sort of thing. Like, I think there are, like Rao-Blackwellization, for example, is one method of reducing the variance of an estimator. And I think that there's a pretty nice unifying picture of all the ways that you can Rao-Blackwellize an estimator by basically doing marginalization or approximate marginalization of variables or auxiliary variables in your model or estimator. But I wonder if and I think like control variates, right? Pyro has done some work on like trying to come up with good interfaces for specifying control variates for gradient estimators, though I haven't looked into it that much and don't know that much about it. But like, I think the question of how to choose a prior is maybe a little like how to choose a prior to make a lost landscape that's nice for HMC is maybe a little bit of a different kind of question. I just because I think like it's a different viewpoint to think you have a quantity that you're trying to estimate and you want to know how to estimate it versus you're going to try to maybe choose an approximate problem. Like I think of the prior as part of the specification of the problem that you're trying to solve. But yeah.
So let me dig into that a little bit. So you mentioned. So I remember when I first started getting into probabilistic programming, and I'd see there's a few papers I saw, Raoul Blackwellization in the title. And I'm like, huh, like that's something that I learned to pass a qualifying exam a long time ago. Like why, how is it showing up here? And so like, so that's when you have an estimator and you condition on a sufficient statistic. And I'm wondering how, but when I saw it in probabilistic programming papers and I would read the abstract, I'm like, well, it doesn't sound like what I think of Blackwell. Could you explain like how you kind of build abstractions around that? And sorry if this is.
No, yeah, well, yeah, I'm happy to talk about it. But yeah,
it connects to me because I'm like, if the issue is like, how do we take some of these statistical theoretical concepts and make them incorporate them into more performance probabilistic programming, or maybe more black boxy probabilistic programming. I'm still trying to get a shape in my head. What that.
So, I mean, I think this idea of conditioning on a sufficient statistic is an interesting example of something where, like, right, that's an interesting phrasing. It's probably connected to the other versions of like what people mean when they say Raoul Blackwellization. Like one way that I think about it is you have some estimator, there's some randomness in the estimator, and you can imagine having that estimator be written as like as a program, right? It's something that you can run, and there's some randomness in that program, right? So don't think of it as writing a model, but you literally have a program that represents your estimator.
Okay.
Right? If you could integrate out some of the randomness in that estimator, it would have less variance. So if there were two normal sample, let me think of like, if you can replace a part of that with like one I'm thinking of the paper that you probably saw with Raoul Blackwellization in the title from like Lawrence Murray about delayed sampling for Raoul Blackwellization.
Right.
And that's in the context of Raoul Blackwellizing an importance sampling estimator. So your estimator is to sample from a proposal distribution, and then you get out an importance weight. And that importance weight in expectation is the normalizing constant of your model, right? So importance sampling is one way to get an estimator of Z, the normalizing constant of your model. The importance weights in expectation are the normalizing constant, but they may have high variance. So any distribution that you sample from, any Q that you sample from, if you take P of X over Q of X, where P of X is your unnormalized target density, P of X over Q of X is going to be an unbiased estimate of the normalizing constant. And that paper looks at basically automating, I think of it as removing randomness from the proposal, but it's actually automating improving the proposal in order to get lower variance importance weights. Any improvement to the proposal, like, is going to reduce the variance of those importance weights and therefore reduce the variance of the estimator. I'm not doing a great job of talking about this off the cuff, and would probably have to have, like, it would be helpful to have a whiteboard and write some things down. But I think that
well, yeah. So I mean, actually, so it makes me think. So yeah, okay. So that makes sense. So, like you're talking, so it's the Raoul Blackwell theorem is about conditional expectation, and importance sampling is about calculating expectations using importance weights. And next, and there are several inference techniques that are calculating weights of some sort. Next, I think Jeremy wanted to read Elias Barenboim's paper on, what is it, risk minimization?
Empirical risk minimization.
Yeah, so that's another kind of, and that's another kind of inverse probability weighting method. So that's another kind, and a lot of And so yeah, inverse probability weighting is about kind of calculating weights by dividing by a probability, and then a lot of papers try and come up with ways of making that more robust by making sure that your variance doesn't explode when you divide by a probability. And so maybe there's a common thread there. Maybe
actually, figure 1 in the TMLE paper does a really nice job of comparing and contrasting inverse probability weighting with TMLE with G computation, and shows you kind of, that G computation is trying to come up with a good estimate of the outcome regression, and IPW is looking at, trying to predict the exposure mechanism, and TMLE combines both of those. And the disadvantages of each of those is because is that neither G computation nor IPW is doubly robust. Now, with that said, I see G computation, TMLE, and IPW, all of them as insufficient for my purposes, where I would like to be able to estimate any estimand that comes out of an identification algorithm. And all of them fall short because they all depend on backdoor criterion being satisfied, right? So there has to be all your confounders have to be measured. And that seems to me like a major limitation of all these estimators.
So if you're thinking of it like, so one good example of how you kind of black box away estimation from a programming implementation standpoint is what's his name? Amit Sharma's do-why library, right, at Microsoft.
Yeah. So, but again, he's not using full identification. He doesn't have any estimators for anything that's non-backdoor. I think he has some instrumental variables. I don't think he even has front door. So if you have latent,
but that would be, but given the interface that he has to his, so if you're not familiar with this package, it's a package where you specify a DAG and you give it some data.
Okay.
And you say what you're looking, and you say what the query is, what you're trying to estimate, and it will provide you with like a menu of estimation techniques. And they're fast, so you go for it, and then you can kind of compare them in terms of whatever you want to compare them with, confidence intervals, stuff like that. There's also some other. I'm really underselling the package. There's some other things. I don't know if it has front door, but given its interface, it would be trivial to add. I mean, not be trivial to implement, but it already has a nice interface for saying like, hey, here's what this is the query I want to answer. Just do it for me. And so like, I guess from you just pick whichever estimation technique you want to use. And you can even do several and maybe can compare them in terms of, I don't know, diagnostics or confidence interval or something like that. I suppose you could do something similar in probabilistic programming, which is kind of just, these are ways of you specify a model, and then you kind of pass some arguments into a black box inference abstraction, and it might just work. I don't know. I'm just kind of spitballing about what this might look like in terms of helping make better about probabilistic programming languages.
So do-why is a good example of a software architecture that kind of tries to abstract away it tries to help the person focus on the causal model. And once you've got a causal model and an estimand, then it takes care of behind the scenes of which estimator you use. I guess it gives you some choices, because it says, do you want to use instrumental variables? Do you want to use this? But it also gives you good recommendations. There's another software package also.
They also it has this really good. They're moving a lot in a way of kind of robust. I guess this gets to what Sam was talking about with sensitivity analysis, but you put in your DAG and it does a few tests to see like, well, how sensitive is your estimator to your DAG being misspecified? Like, what if there were some confounding between two variables in a model, for example? It does that as well. So
right,
anyway.
It tries to do refutation, right?
Yeah, I think that's what he calls it.
Yeah, he calls it refutation. Right. So I agree with you. I think that I think Pearl has this kind of vision of a causal inference engine. He's got a picture of it in a couple of his papers, where he kind of describes, you've got your causal question, you have your kind of prior knowledge, and you have your data, and you can generate an estimand even without any data. But then once you have data, then you try to estimate that estimand, and and you can also, if you have data and just a model, then you can ask, how can I refute this model from the data, right? So that's the testable implications section of his causal inference engine. I don't know if anyone has or who is sharing the screen.
I know what you're talking about.
Yeah.
Okay. Do you need the rights to share? So we got to enable that or something.
So DoY, I think, does a good job of trying to implement that vision. Although I still say it falls short because it doesn't. I mean, so I guess Sam says it now does have front door, which is great. But there's another software package which I'll just put in the chat window that called Ananke, which is the Greek goddess of causality. I didn't even know such a mythical figure existed. But this addresses the question. So first it has this one-line ID algorithm in there. So you just say, is this DAG identifiable for this causal question? It goes yes or no, right? And then given that, it gives you, it says, how do you want to estimate it? And then it gives you a choice of estimators based on the complexity of the DAG, right? So not just a DAG, a mixed graph. It's ADMG, so acyclic directed mixed graph. So it contains bidirected edges that imply that there's an unobserved confounder between two variables, and it figures out. So if you, I think I put the link to the quick start in there. You can immediately kind of choose a different estimator depending on your DAG and your causal question. So I just discovered this last night, and I was super. Oh, I can share my screen. Okay, cool. Yeah. All right. So I feel like now, because I think that the advantage of TMLE is that it's kind of an automatable estimator, and that's the same advantage that this semi-parametric approaches have in Ananke, is that it automates the process of estimation, right? So it takes into account double robustness and there's a number of really nice properties of each of the estimators. There's like four different estimators that they include in Ananke, and each of them kind of deals with progressively more difficult ADMGs to actually identify or to estimate from data. So I apologize. I realize I'm a little off topic here because I'm jumping to the semi-parametric one. But I think we're talking about software architectures that could, in principle, include estimators that are not, they could include like a whole library of estimators, even including ones that have that can handle any identifiable query, right?
Right. So I think one important gap between DoY and what it sounds like Ananke is doing is that DoY is look, the user specifies a graph, right? But then given that graph, the library is looking for very specific templates of causal structure. Whereas it sounds like Ananke is really, it's more of like a programming model where, I don't know, the assumptions that the user specifies are almost interpreted. I don't know, I have a better way to think about it, but it feels closer to what we want, I guess, just based on that.
I think so too.
Yeah.
But I like the vision of DoY. The implementation I still feel falls a little short. Ananke, at least, impressed me, at least initially, as having the right kind of approach, of implementation. I'm sorry, I'm reading Alex Liu's comments here.
Oh yeah, sorry, this was going back a little bit, but I think the Rao-Blackwellization pattern is taking any part of a randomized computation, so like some randomized computation that's supposed to output some estimate of something, and replacing a block of code in that computation that may sample some random variables and then assign a local variable to some function of those random variables with just the assignment of that local variable to its expectation, or to its conditional expectation, given everything that you're not deleting from the program. And this results in a lower variance estimator overall.
Right.
And in the context of the Rao-Blackwellization paper, the randomized algorithm is the particle filter, that the probabilistic programming system is implementing. And they're taking out a part of the portion of the computation that computes the incremental weight and replacing it with something that just deterministically computes the expectation of the incremental weight for that step. And like for each step of the algorithm, conditioned on the variables that they're not marginalizing out.
That would definitely reduce I think that makes sense. And that's really kind of what Rao-Blackwell is saying. If you have some sufficient statistic, you can just condition on that, and all of a sudden you get a better estimator, right?
Right, and the expectation
at least
is sort of...
Sorry.
Right.
Well, you would have lost points on the qualifying exam.
Oh, sorry. Well, what did you say, Rob? I didn't hear you.
At least as good as the original estimator.
Right.
At least as good, not better than, right? Fair enough.
Not strictly better than, probably,
Probably.
usually better than, yeah.
So I want to circle back to something, Robert, that you said early, which seems to imply that sort of like separation between computational and statistical thinking. And I wonder, one, if that's an accurate representation of what you were saying. And two, what should that demarcation line be between the statistical and the computational here?
Yes, I suppose what attracted me to Pearl's version of causality, and you wouldn't know that this was a feature to ask him, because I don't think he's aware of it, but is this clear delineation between causal semantics and statistical semantics, right? If you ask Pearl, he uses do calculus to identify some estimand, he could give a shit about what your estimator is. He just cares about identifiability of the estimand, right? And because once you've shown something to be something to be non-parametrically identifiable, then you've reduced the problem to a problem of statistical estimation, right? Now, of course, you can go beyond that with things like instrumental variables and get some variants of parametric identifiability, and that's important. And so that's where the lines blur. But in terms of non-parametric identifiability, you have a nice clear line between your causal model and your the statistical nuts and bolts you use to actually get a number. So that, and in other words, once you get identifiability, then all right, so how do I actually implement this thing? What's the bias versus variance trade-off? Does it scale? Can I get it to work on 1 million data points? Right, like that's another problem. But it's problems that we can just kind of refer to the traditional kind of computer science and statistical estimation literature to solve. Similarly, in probabilistic programming, I'm a huge fan of kind of separation of abstraction between modeling and inference. One abstraction that I see that kind of irks me in a lot of probabilistic programming languages is when they like in the model you specify X is sampled from this, comma, obs equals some data point, and I'm just like, oh, why are you adding the data into the specification of the data generating process? I like it when you have modeling over here and inference, guide functions and conditioning and soft conditioning and whatever on the other side. Things that mix them together, like kind of bringing data into the model, or factor statements, stuff like that. I'm not a huge fan of, and so like yeah, so I think it's just a personal preference, but to me there's a duality there, a separation of modeling and inference, and a separation of causality and statistics.
Is it more complicated in probabilistic programming languages because when you're hoping to estimate causal effects, it has to do with the structure of the program? And it's easier in the context of classical inference that observations can be specified outside the program because you don't have to change the structure. You don't have to deal with the structure, basically. You can write your program and then say, okay, construct a choice map. I want to observe a few set of latents here, right? Whereas with a causal query, maybe I'm mistaken, but I thought that you would have to reason over the structure of the program, and it's more difficult because you can't it may be tougher to abstract over that dimension.
You could imagine a specification language where you're allowed to use uninterpreted functions, or like you can definitely have a language for structural equation models where you're only allowed to say f and epsilon, and you're not allowed to, inside that language, specify the forms of any of those functions, right? You could imagine doing something like that. It would be interesting to think about what the benefits are of doing something like that.
I think that's basically how these two packages in Anke and
right.
work.
Right. And maybe you could completely generalize that to the full set of probabilistic programs, and still come up with a language for structure of computation versus data. Though maybe you get into the same problems that you get into when trying to separate types from values in programming languages, where I don't know, there's probably ways of blurring things, especially when you're doing complex data dependent control flow. But
you could also write a program, so to use your example of, what did you say, f and only allowed to use f and epsilon. Or you could write a program and then you write some kind of, there's some kind of operation that creates a version of it that's just f and epsilon. Yeah.
Right. Yeah, and I think that's really especially right. I think the problem of detecting the maximal number of conditional independence relationships to be able to encode into that model is an interesting problem, right? Because you can always write a program where each variable is sampled sequentially based on all previously sampled variables or something like that. But that's not capturing the causal structure that's latent in the program that the user wrote. And in general, it's probably undecidable to do that perfectly, but you can get pretty far using partial evaluation. There's a chapter of there's a section in the textbook, the Introduction to Probabilistic Programming textbook from Jan Willem and Hong Suk and those people. That's about compiling a first-order probabilistic program to a Bayes net, and that a similar question comes up of how do you decide what edges to add in that Bayes net? And they show that you can, if you're too conservative and you just look at which variables are used where, you can add too many edges. But if you use partial evaluation to for example, think about the shapes of the arrays and the indices that are being accessed of different arrays, then you can make a better Bayes net with fewer edges.
I really wish there was more research in this area. I feel like if you don't come from a deep PL background, it's a bit of a Sisyphean feat trying to take this on by yourself. So Please tell your PL friends.
What would, I mean, I guess one question I have about that is like, what are the, like, I think it would help to know more about like what the desired use cases of that kind of technology are. And like, I can think of some, like automating inference algorithms that take advantage of the conditional independence relationships. Seems like
that seems
an
like a huge
important
use
one.
case.
Yeah.
I guess, I mean, the question, yeah, I ask myself, there have been times that I've been writing probabilistic programs and I wish that I knew, oh, sure, okay, so like if I have some kind of domain knowledge that I might want to encode in the form of, as a constraint on my probabilistic program, and so being kind of really loose in my terminology here, but say if I have some kind of domain knowledge that where I know that I expect certain things to be conditionally independent, be nice if I could just kind of, you know, blacklist some sets of dependencies, and you know, especially so yeah, especially in a kind of you know, Bayesian program synthesis type of issue. So we've done a little bit of this at Gamelon and have had some good results. But I always feel a bit kind of guilty as somebody who, you know, did his PhD in causal inference, that there's known conditional dependencies here that I have no way of constraining in this very, you know, which in a problem that's a very tough search problem, it'd be really nice to constrain that space a little bit.
Yeah, the BaseDB project that was sort of worked on by Faraz and Uli and Vikash in our lab before I joined, is a little like, it's a particularly simple sort of Bayesian program synthesis for modeling like tabular data, where it tries to learn a model automatically of some tabular data and non-parametrically, and it includes a language where you can specify independence relationships that you want to use to constrain the inference process of inferring a program. But it's a pretty simple language. I don't think you can't express conditional independence, only independence. That's one thing, because the models that they learn don't have very interesting conditional independence structure in the first place.
But even that was a big deal. I remember when Veronica showed me that, and I was like, that would be quite useful.
Yeah, but I think constraint languages for generative processes, instead of requiring the user to write the generative process, right? Constraint languages that specify qualitative constraints on generative processes, and then synthesis algorithms that synthesize things that are consistent with those constraints is a really interesting direction.
I think Fritz Obermeyer had tree cats or something like that, or he had something, or one of his repos is along those veins. I don't know if he's worked on it for a while.
It does sound really useful. So can you put a link in the chat for that constraint language?
Yes, I can try to find the
tree cat.
There's tree cat, and there's I think they called it their meta modeling language for BaseDB.
Oh right, that's right. Oh.
So
remember that.
Here's like the BaseDB tech report.
Could you do that with Venture?
I don't know if they actually used Venture in the implementation of, but you are allowed to use Venture code in order to like manually fill in parts of a model that the rest would be synthesized around, I think. Or that was some of Faraz's work.
Just to ask, so the interest there was declarative languages for declaring independence assumptions. Is that right?
I mean, yes, and although I mean, I don't know who goes around just looking at things and thinking about what's conditionally independent of what. That just seems like not a particularly intuitive way of thinking. But So there's probably some kind of interface to that that's more intuitive. But yeah.
And so Alex, you're saying that BaseDB is an example where you might declare those sorts of relations and then a non-parametric model is learned or synthesized? Okay.
Yeah. I mean, I think it's this paper, or I'm not claiming that BaseDB solves the problem. It's obviously a huge problem that BaseDB does not solve, partly because the class of algorithms that it synthesizes, or the class of probabilistic programs that it synthesizes, is quite limited. But it's I just think it's an interesting example of the idea of a meta modeling language, or like a constraint language, which would allow for specifying causal assumptions, or like the independence relationships implied by a causal graph or something, and saying, I want to synthesize a model based on data that obeys these assumed relationships.
One thing, so we're almost at time. One comment on we are at time. If we, people want to, I brought up Bayesian program synthesis. People I have no idea what the state of the art is there nowadays. I think Zedam had written something about that recently, but some people want to suggest some papers to read kind of down the line, and that, because there's clearly a relationship between Bayesian program synthesis and
causal structure discovery.
Yeah, but and those are definitely two communities that don't talk to each other.
Causal structure learning causal discovery is a bit of a rabbit hole.
Yeah.
Yeah, so we should be very careful about exactly how deep we go down.
The group to go in that direction.
Especially once you start to consider latent variables, which is pretty much the only use case that matters. But the paper that I have here for next time, I think Sam, you said not to read it because it's a book. So what should we read?
Well, I think that depends if people are psyched about this semi-parametric stuff that we read today. I'm getting the impression no. This is one of those like absence of excitement sort of.
I'm unpsyched.
Well, I think it would help. Maybe we can just, I don't know, like, do we want to talk a little bit about what we want to get out of this group? I think we had a little bit of discussion about that at the beginning, but it might be nice to revisit that question and thinking of it. Sorry?
We could have a kind of recap session, looking forward. Good way to wind up the year.
Yeah, it's so what, next Monday, when's Christmas?
Friday.
Thursday. Friday, okay. So
so yeah, that's another question. Do people want to meet Monday or
like
pick it?
Okay.
Yeah.
Open.
I'm not going to be doing anything. I'll be on holiday.
Yeah, I'll be around.
Eli, did you say that you wanted to go down that rabbit hole, or you didn't want to go down that rabbit hole?
Well, it's a democracy, but I think it's a decision that should be taken. We should make a bit of a commitment to it if we're going to do it.
Right.
And that we devote 2 or 3 weeks to it, and also.
I don't know. So causal discovery algorithms, it's useful to know like the high level stuff like score based versus constraint based and all that. But at the end of the day, most of the papers you see are just kind of, if you're not working with latent variables, all they're doing is trying to get it to scale to more nodes, really, or make use of, say for example, let's assume everything's linear. So it's like, there's really a lot of just trying to get it to work better, as opposed to kind of really the abstractions tend to stay the same. Once you start factoring in, if you start trying to infer structure under latent variables, which obviously is the situation in most settings, then it gets a bit gnarlier. But I think it's possible to touch on it without going, too deep into the nuts and bolts.
Is also an even deeper rabbit hole.
So I think we have a number of choices, right? So we at least what we've discussed, we've mentioned we could do more semi-parametric methods. We could do causal discovery. We also mentioned sensitivity analysis. And that was something that Eli had mentioned, and I think
Sam suggested it.
Sam suggested it, right? And that seems like a really kind of fruitful area as well. And it kind of touches upon the testable implications kind of question, right? So you have a causal model, you have data. How do you know it's any good? Can you repair it if it isn't good? Which is different from causal discovery, although they're related, right? Because if you just assume knowing nothing, then causal discovery gets you there. But if you have already a mostly complete model that may be misspecified in certain areas, how do you find where it's misspecified and just repair that, right? So I like sensitivity because I like to be able to leverage as much prior knowledge as possible, and I feel like causal discovery is in some sense a bit too tabula rasa for me. So I'm really interested in the sensitivity analysis and trying to understand how much we can leverage from our prior knowledge to repair those parts that might be wrong, right?
Yeah, I mean, I think a part of whether we go for sensitivity analysis depends on the answer to Alex's question about what the role of the group is. Because last week I sort of posed that topic as like hey, do y'all want to write a paper together in this large sort of collaboration? So if the answer is yes, then yeah, we should probably read some of those papers if that's the topic to write a paper about. I mean,
yeah, I think it would. Oh, sorry, go ahead.
Well, I was going to say, for just to give some context for myself, like I realized today a lot of people here are post-PhD, and I am not a post-PhD, so I feel like I need to stay focused on cranking out work. Maybe that's a little selfish, but anyway, yeah.
I'm certainly open to writing a paper together. I think that'd be really awesome. And with all of our expertise in all your guys' expertise, because my expertise is not in probabilistic programming languages, but I'm very interested in that area. What is it that you think that we would want to talk about? I mean, there's this kind of interesting relationship between probabilistic programs and causality, and we've already talked a little bit about how, in some sense, a probabilistic program obviates the need for identification. It obviates the need for efficient estimators. It's a whole different way of thinking about causal modeling that maybe is underappreciated. And maybe we could just talk about, all the different ways that probabilistic programs kind of address the same problem from a different perspective.
I'd be interested, like paper or no, I'd be interested in coming up with a set of questions that we're interested in thinking about, like to maybe lend a little bit more direction to like the reading and discussion. I not that, like, I think we can probably read a bunch of different papers thinking about any of these questions, right? So it doesn't necessarily dictate which papers we read, but it would be interesting, at least to me, to see if there's common ground in terms of what burning questions we're hoping to answer with this reading, or like gain clarity on for ourselves with this reading.
Yeah, I agree on that. I think we should use next week to clarify the things that we care about and our intentions. I mean, I think personally, like I have maybe dual interest. On the one hand, there are all these areas in causality which we haven't so much touched on so far, right? Things, other causal questions like actual causality and explanation and so on. But at the same time, I'm interested in just all the stuff which, some of you are experts in, which I don't know about, like things like, like today's paper, for instance.
So how about we just, I'll make a little quick survey now. We can send this out. Like, so what are?
Let me just ask quick questions. Sam, was your comment? Were you saying that you wanted to, focus and collaborate on a paper, or that this reading group was taking up time?
No, yeah, I think I sort of misrepresented what I actually feel with that comment. Like, I'm not saying
PhD is hard.
Sorry?
PhDs are hard and you don't have any time to do anything.
Well, I'm definitely not saying that I don't want to, explore ideas as a group. And I think, Zena, Alex, as you mentioned, there's a lot of people here who know a lot of things that I don't know, and it's like super valuable to just sit and talk. I think the more, it's not a waste of time, but it could be even less of even more valuable if it, if there was something more focused in the center of it. My foot is still in my mouth right now, by the way. I don't feel like I've gotten it
I think
out.
what you're saying makes perfect sense.
Okay, thanks, Alex. Thanks for backing me up here.
No, but I think it does make sense, and I also think that maybe people do have different perspectives. Like, I didn't come into this thinking any paper's going to come out of it, to be honest. But I'll be happy if a paper did come out of it. But that certainly wasn't. I mean, it would be hard to write an 8-person paper, but it's definitely it's definitely possible.
Right.
So me personally, like I do not have an agenda of writing more papers. I tend to work with people on writing papers because ideas need hashing out. But I'm an engineer. I'm interested in what powerful things I can do with probabilistic programming, and how I think that there is some kind of killer app in terms of causality there somewhere, and I want to build something with it. And my goal, and that's partially professional interest, but also because maybe I want to turn that into a business or something like that. So so I'm much more thinking in terms of real world impact. Not that papers are impactful, but and again, I'm not allergic to writing papers because, like I said, sometimes you have an idea, you need to push it out.
Yeah, I'm interested in. I mean, I think maybe one way of looking at the papers thing is that I'm interested in identifying opportunities for interesting research to happen, right? And whether and reading in a direction, I don't know, like a paper like today's could be a really important piece of evidence toward developing some hypothesis or answering some question about the way, what kinds of computation are necessary to do causal inference, right? And I'd like to have specific questions in mind reading these papers, because the danger, I think, is that we can read it, sort of get to know that this exists, but not have probed at the right pieces of it to be useful for whatever intellectual journey that ideally this reading group is taking us on. And it makes sense that that people could have different questions that they're interested in, but it would be good to sort of put those out on the table. Just so we know what's going on, because I'd like to read with more intention, not toward a paper, but toward answering questions or developing opportunities for probabilistic programming to be more useful, which I think could naturally lead to papers, which is why they're the activities that as PhD students were maybe particularly attuned to.
Mm-hmm.
This is my first meeting, so I don't necessarily think I have a strong thing to say about the direction of the group per se, but I think I mostly agree with Alex. I'm pretty focused on system stuff, and I guess the reading, I tend to want to think about it from a perspective of how you could incorporate it into systems of the future, or how techniques might be unified into, I think, similar to what Alex was describing earlier, programming language abstractions. So from that perspective, I think it's interesting to look at the literature and sort of think about, okay, so what sort of frameworks, what sort of techniques can generalize and potentially we can build systems on top of. I don't know how that affects the direction of the group, but
yeah, I see a potential outcome as code that's generated as a result of our of our collaboration, right? We could write systems. That'd be also an awesome thing. So publications, code.
Yeah.
Yeah, I think it's interesting to me because I know that there is existing systems which have some causal inference techniques, like for example, Pyro, Eli, in terms of I think causal graphs, or I've seen that there are mentions of causal inference in the Pyro system, and I've discussed with Zena causal inference as an aspect of Omega previously, and I guess I'm kind of interested in the future in how I guess what's missing from these systems, why these components or elements are not bigger parts of the use cases that these systems are sort of aiming at. And I suspect I don't know enough to really make a good analysis of what is missing, why it's difficult to use these aspects. But yeah, I think that's a good summary of my interest.
I don't know. I mean, personally, I read all these papers with the same question in mind, which is, that I have a working hypothesis that most of this literature can be compressed into a few, maybe even not that interesting PPL components. That the questions like identification reduced to questions about mechanical questions about conditional independence, right? And we can reduce all these funky estimators to various sorts of inference in modified probabilistic models.
So it would be interesting to have that be an explicit part of the discussion. Like, did you feel that way with this paper?
Yeah, well, I think people took the discussion in different directions, but I think it's useful to understand at least G computation and inverse probability weighting as as complementary estimators for counterfactuals or causal effects, right? And you can place those in a kind of a model-based context, right? They're complementary in the sense that, say given a DAG or given a probabilistic program representing a causal model, probability weighting corresponds to a particular, you're estimating a particular posterior distribution, and then G computation corresponds to estimating a particular marginal distribution. And there are lots of ways of combining Monte Carlo estimators in ways that reduce variance or are robust, things like that. That's also why in past meetings I'm always harping on thinking that that these causal DAG abstractions are unhelpful at best.
So two follow-up questions to that I have, and I think that's really helpful. Is one, you talked about G computation and inverse probability weighting as reducing to these problems of P of y given A and X and P of A given X, right? And one question is, should everything downstream of those estimation tasks sort of be outside of the probabilistic programming system? Or should the probabilistic programming system give you the means of combining these estimators or transforming them into estimates of the ATE and thinking about ways of optimizing that estimation, right? Like by reducing variance or other sorts of things. The second question is, like, it's true that you can look at inverse probability weighting and say, oh, there's the subproblem, which is P of A equals 1 given X, and we know how to use probabilistic programming for that. There's another view, which is that inverse probability weighting is computing that in order to do importance sampling, essentially. Like the inverse probability weight is an importance weight where your proposal distribution is your observational data, where it came from, where the like the actual distribution that you got is that some people were A equals 1 and some people were A equals 0. And you want it to be, you want to do an estimate where you're targeting a different distribution, like uniform on A. And so you weight by 1 over P of A equals 1 given X, or P of A equals 0 given X. And there you can imagine like probabilistic programming abstractions where the importance sampling is inside of the system, where the proposal distribution is the world, but you model the proposal distribution somehow. And you learn the parameters of the proposal distribution from the data that you say were simulated from the proposal distribution. And then the weighting happens automatically, right? And being able to put more of that computation into the probabilistic programming system and into the, like, I don't know, it makes the justification for these algorithms clearer, maybe.
Here, I also, you know, I also suspect that again, one could achieve a more systematic version of the variance reduced marginal estimator for the average treatment effect by combining writing down some sort of extended model where both counterfactuals are that contains lots of interventions.
I think that's equivalent to GComp, because you're imputing counterfactual outcomes based on your conditional distribution of outcome.
Well, the point is you want to share importance samples or statistical strength between your estimates of instead of averaging your two unbiased estimators, you want to estimate the average, right? So the equivalent, the PPL version of that is to put everything into a, try and put everything into a single extended model.
Right.
I don't have profound thoughts about how to do that, but again, I suspect if we're, in keeping with my underlying motivation of thinking that there, is a relatively small set of relatively simple and straightforward ways of thinking about these things as modifications and inference in probabilistic programs. That's a useful way of thinking about this class of estimators that includes the targeted learning estimator.
Yeah, I think that's super interesting and would love to read these papers with an eye toward trying to come up with satisfying embeddings into some simple set of primitives.
This is also why I like Omega so much, because it's probably the closest thing to, it's probably the closest system to achieving that, the goal that I've described.
I wonder, like, both of your comments, whether this notion of an estimator should be a first-class notion in probabilistic programming languages, because it isn't at the moment, right? And I feel like maybe it should be, or at least for some people. I don't know.
I think that's different from like the conditional expectation in Omega.
Sorry?
What do you see as what distinguishes an estimator in Omega from, or potentially an estimator from a conditional expectation?
Well, you could imagine, like, I guess going to Alex's point about being outside of the model, right? You could imagine, actually, I don't know what you could imagine. It's hard to think about. But I guess, going to this question, can you potentially automatically construct these estimators, right, independent of any particular model? Seems that there must be some like need for some space there in some way. But I'm speaking vaguely because I don't really know what that would look like. One slightly related comment is going back a little bit earlier to this question of like, defining conditional independencies versus how PPLs work at the moment. I think there's this tension of like that PPLs for the most part are fully constructive, fully generative, right? And so if you want to add a constraint, whether that be about conditional independence or otherwise, there's this kind of tension between like, all the conditional independencies of your PPL are already defined as soon as you've got your model. So what does it mean to impose additional constraints on top, right? If you're doing something like Bayesian program synthesis, where you're really constructing a new model in the model, then that kind of makes sense. But otherwise, in order to add declarative constraints, you need to abstract and have some freedom, right, to be, for that to make sense. And this ties a little bit into this RCD, the random conditional operator that we have, because that in some sense allows you to take a model and then lift that to a space of models and then impose constraints on top, right? So there might be an interesting way in which you could actually impose conditional independencies on a model through that mechanism. But that may not make sense unless you've looked at the RCD mechanism.
I think to the question of conditional expectation, like I think if you have a language that has this RCD feature, as in Zena's work, you can imagine program transformations that say, oh, if I'm trying to, and maybe you already have some of these, Zena, that says, if I'm trying to look at the expectation of f minus some conditional expectation of f minus some conditional expectation of g, right? Then we can combine those into the expectation of f minus g. Right? This is similar to the thing that Eli was talking about. That could be a program optimization that you can't do with like divided by, right? Because because an unbiased, right? You don't. Expectations don't work that way. And I can imagine trying to think of more program transformations that happen at that level and like trying to frame more of these estimators totally inside of the modeling language, or estimate like things that you're estimating inside of the modeling language, and thinking about what kinds of program transformations, even in simpler languages than Omega, if that helps us come up with good program transformations, right? And some of, like, if you look at some of the work on exact inference in, for example, Lambda Psi at PLDI last year, they use examples that are kind of about nested expectations, because if you have exact inference, you can just have expectation be an operator in the language and compute it when you need to compute it. But thinking about how you make that work with without exact inference is interesting. Or how you can use exact, like, I think some of what Zena's work does is recognize certain cases where exact inference is possible for the sub-problem of computing the expectation and then just compute it. So all of that could be interesting to apply in these cases.
So I was really curious about that. At a language boundary, where you might have a language which supports exact inference, but another one which supports only approximation-based inference, and how do you cohesively present these operations to someone who's designing their model?
Well, I think you want to do something like what Pyro does, right? Like Funsa does, right? Like you want to be able to take your model. I don't think you want two languages. You want to interpret your model in different ways. Yeah. And so
I think. Oh, go ahead.
No, I was going to say that. So we have some simple kind of transformations just to compute expectations exactly, right? It's a subset of the tractable cases. It's just like the set we can pattern match on, basically. And I think Funsa takes that to a more general scope.
Yeah, I think there are arguments for both. I think there are benefits you can get when you have limited languages that you have algorithms to process that don't require recognizing when you're in a case where your algorithms can process them.
Yeah. That is a tension though, right? Like, yeah, I guess I'm not sure. Like, maybe there are some hard technical questions that, like, what is the recoverability of some structure, right? So let's say you encode some conditional independencies in some general PPL, right? To what extent is it possible to, uncover the required conditional independencies to have some efficient algorithm? It's not obvious to me.
Yeah, I think in general, it would be uncomputable, right? Because it's like a non-trivial property of a program. But in restricted languages, probably you can get more. And you may just be able to do analyses that are not complete but are sound and cover the vast majority of cases that people do, even in a very full-featured language. I think that there's like an intense interest in automation of all sorts of things that I feel like my gut reaction is to think that automating those things would be really cool, and I'm interested in them as research directions, but also sometimes those things are the things that the person really has no trouble knowing and specifying. And so you're not actually winning a lot by doing it unless you're suddenly going to be able to apply it to some really large-scale program. But then in those large-scale programs, like, is inference going to work in the first place? So I feel this way sometimes about structure learning too, that like for many models that people want to write, they kind of have some idea of the overall structure. And like, it's much better to provide automation of the parts that are really hard to encode as programs than the parts that are really easy to encode as programs.
Or else they have a very, very strong assumptions of regularity on the, maybe there's lots of structure, but it's very regular. Like they want to learn the structure of some gigantic Gaussian graphical model.
Right.
Cool. I sent over a link to a survey. Use that to kind of collect some ideas. So we'll just kind of talk about the survey next call and skip the paper. Or is that what we're doing?
Sounds good. Oh, but I'm getting a you need permission, by the way, Robert.
Oh. How do I do that?
I mean, it sounds to me like we almost need to spend some time understanding the architectures of some of these probabilistic programming languages and what's kind of unique and different about them, and also, as you were saying, identify gaps that none of these causal programming language, causal enabled programming language, probabilistic programming languages can handle, that would be needed for a full stack causal reasoning system, and kind of identifying what those gaps are as well as opportunities for innovation. Does that sound like a reasonable direction, or something we should include on the Google form at least, and possibly come up with examples? I mean, you guys mentioned FunSir and of course Omega. Everybody, maybe everyone's already read the Omega paper, but it would be useful to have maybe a discussion about what's specifically unique about Omega that Eli likes about it so much, or something like that, where we kind of dissect what's there and what still needs to happen.
So Robert, now I can access the form, but it's to help me edit the form rather than. Yeah, no worries. These things are.
We can certainly go into those details if people are interested. I think I would kind of return to David Jensen's point in the very first meeting that we had, that our systematic theories of causal reasoning don't align very well with the sorts of causal reasoning that are actually done to solve real problems. And nobody's the number of working statisticians or epidemiologists or whatever using Pearl's textbook is pretty much zero.
Right. So how can we? Well, I think actually one of the main reasons
we would also productively spend time understanding what these people are actually doing.
Yes, well, that's true. And I think one of the things that really brought my attention to that is, the things that statisticians care about are like, is my estimator doubly robust? Is it, is it efficient? Is it, does it work in low data regimes? And none of that is kind of part of Pearl's causality. In fact, they just kind of leave it as an exercise to the reader, as Robert Ness was saying, to find an estimator for these identifiable estimands. And so I think one major thing that can be done to bridge that gap is to take a look at the the weighted empirical risk minimization paper that Barenboim just recently published, or the semi-parametric approach that Ilya Spitzer's group came up with as a way of bridging that gap, because they actually do care about the kinds of things that statisticians do care about, and they try to address those issues, but they do it in a way that's fully robust to that fully accounts for unobserved confounders that the TMLE just can't handle.
Yeah, I mean, I'm not adverse to, so for one point, I'm not adverse to reading that paper. I still maintain that standpoint that, like, if you're an actual practitioner, you're going to be looking, once you have a problem in front of you that's specific to whatever it is you're doing. Maybe you're doing PKPD models in pharma, or maybe you're doing survey data in some kind of social science. You're going to pick whatever causal inference estimation method the other people in your subfield are doing. So I think trying to stay high level when it comes to estimation, to me, just seems like, that itself seems impractical to me, because in reality, people are going to just zoom in on one particular method for their design. And so, so I'm less enthusiastic about that. And and in terms of, when I started teaching my causal modeling workshop, I thought that I'd get mostly like machine learning people who maybe, because they're coming from a computer science background, might be more favorable towards my bias towards Perl. But that isn't the case. Like, over half my students are coming from economics or from social science and are wanting to understand more about DAGs. Couldn't explain to you why, but usually it's because they, especially the economists, they learn a very narrow subset of methods, like difference within difference and regression discontinuity, and they're trying to understand, like, they don't really have a good grasp of the whole problem of causal inference, so I humbly disagree with you, Eli. I think that there are a lot of practitioners out there who
but the identification strategies that economists use, right, are specifically not captured at all by Pearl's framework, right?
Can I add a third way, like my interpretation of it?
You can't write down a difference in differences model as a causal effect on from a DAG.
Propensity scores, you can. Some of them we can. Some of them, at least it's clear to me, like propensity scores is just adjustment, just forward adjustment. Like
instrumental variables, right, is the other big thing they use. And
instrumental variables, you can definitely explain.
All those things are not.
Instrumental variables, you can definitely characterize with DAGs. It's just independence assumptions that you get from, and then you can define it in terms of a DAG. Like you can define what an instrument is in terms of a DAG.
Yeah.
So my impression of the practice of causal inference is that people, economists, social scientists, epidemiologists, they read books like Pearl, and they use it to get a mental model of, causal thinking. And then they go into the world and they apply regression discontinuity designs, instrumental variables, and use the formula they've, or just any, off the shelf regression, making sure to think about all the causal considerations in their head, but it's not really explicit in their analyses.
But I think
that's my view.
I think that's just a consequence of not having any good estimators for any identifiable causal estimand. If you don't have any good tools, then all you're limited to is conditional ignorability, then there's no reason not to use all the really awesome tools that the potential outcomes framework provides for estimation, right? It's only if you have an estimator that can estimate things that you couldn't even ask using the potential outcomes framework that you would actually want to do that, right? That you'd actually could go full stack from a causal question to a diagram to an estimand to an estimator to actually estimating it from data, right? And only now in like this year, 2020, has that even been possible, because there were just no estimators until this year which could do that. And now we have two, actually a whole slew of them, about half a dozen at this point.
Let's see if I can invite some of my friends from like the Bay Area who specifically on causal inference problems at tech companies. And some of this call might be a useful contribution to the group. Some practical, I only know a few, and they're definitely using potential outcomes. Every single one of them.
Right. I mean, what do you have if you're trying to estimate, causal effect from data? You don't have the option of using Pearlian causal inference because there's no estimators for it, right?
Well, I think the more common reason that people don't use that stuff is that they don't believe in their conditional independence assumptions, or they don't have it.
Yeah, that's why. I mean, like once you have the estimand, you can create a model, and then it's for the estimand. That's not, and then you can figure out just using. I mean, these people who do that, they tend to be good at statistics, and they can figure out how to, get the bias versus variance versus computation trade-offs that they're looking for. Yeah, so it's not the estimation that's hard for them. It's belief in the model that's hard, which is why robustness is such a huge theme there, because they want to kind of feel safe about being, like, even if something that some of their assumptions might be off, they're still they're still safe. That's a big fear. Being specified wrong. Model misspecification is a huge fear.
Yeah, and that's why hierarchical models are so popular. Exchangeability is such a powerful source of robustness.
Really, you don't think that it's advantageous for econometricians or epidemiologists to actually make their assumptions explicit as a causal DAG?
I guess my point is that often those, they don't have those assumptions. Like,
you don't think they have domain knowledge that they want to apply to the situation? I mean, that's what, as a computational biologist, I'm always trying to leverage whatever domain knowledge I have to understand, the data that I've been presented with, which is usually like severely underspecified and requires a whole lot of domain knowledge just to even be able to make sense out of, right?
Yeah, I mean, I've wrestled with this question myself. I mean, and then there's that results that I think Shokoff mentions in his book that that's these potential outcomes in Pearl's framework are inequivalent. So if you're relying on potential outcomes assumptions like, I don't know, ignorability, there's an equivalent, exogeneity, these things, you're still kind of translating these over to, in some way or shape or form, to a DAG, although you may not be realizing it. But yeah, I mean, I just talked to Sean Taylor at Lyft, or forget what his name is, a guy who runs kind of the algorithm, some of the statistical decision-making stuff at Facebook, and or like Jeff Long at Netflix, and yeah, they're just they don't like the idea. Drawing a DAG is great for communicating stuff, but going beyond it to actually rely on it in a model that you're going to deploy and is going to, and where there's money at stake, something that people aren't comfortable doing. This was a big theme last year at that MIT conference. I think it's called Recode or Code, or either Code or Recode. But so it's a conference on digital experimentation, and there was a big panel with you can probably find it online, but it was a panel with some of these folks as well as some eminent potential outcomes people from academia, including Susan Athey and a man from Harvard School of Public Health whose name escapes me. But they were very much anti-DAG, even though, I mean, you know, or going beyond the DAG, other than using it to specify kind of simple toy models with basic assumptions.
I mean, I don't understand why they were anti-DAG, I guess, and it's hard because Susan Athey's not here, right, to defend such a claim. But to me, it seems absurd not to use domain knowledge to be able to specify your problem, right?
Well, I think lots of domain knowledge doesn't exist in the form of conditional independences, right?
I think, you know,
I can't imagine
maybe
writing
a conditional dependence, but it exists in the form of arrows that you draw between circles, like clicking causes, you know.
I think that's just how human beings think, is in terms of causal relationships. And having a DAG framework is just like a really obvious, intuitive way of representing your kind of qualitative knowledge, right? And then you're right, you don't represent conditional dependencies as your domain knowledge. You represent this causes this causes this, and it's the absence of the edges that implies the conditional dependencies. But that's 2 steps away already from your domain knowledge, right?
But Jeremy, how would you write Newton's laws as a DAG?
It's an SCM. It's very easy. It's only 3 variables, right?
But does the structure tell you the whole story?
It tells you enough of the story that you already know what the conditional dependencies are, right? In this case, none, because it's a fully connected graph. But I think the interesting thing about Newton's law is that if you just look at it as an equation, then mass could be a function of acceleration and force, but really that doesn't make any sense. We know that, right? It's only that force is equal to a function of mass and an acceleration, and that you change the acceleration, that's going to change the force. And those are the so there is actually in our minds, even though they're equations, they do have a direction, right? And so there is a DAG there.
Well, there's sort of a DAG and there sort of isn't. I mean, like Newton's law, force equals mass times acceleration is like a template that can be instantiated on different objects that are colliding with each other, right? I mean, how do you communicate the symmetry of forces acting on 2 objects that collide? I guess the point is that there's richness in the domain knowledge that doesn't seem to be captured by a DAG, or at very least not by a non-parametric specification of a DAG.
Yeah. Also, I mean, when looking at some of the causal inference problems that I was working on a bit at Uber, we didn't know the DAG. There was no, it would have been hopeless to write down a causal generative model of interactions between drivers and incentives and riders and holidays and whatever. What you have is a bunch of features that are meaningless to everyone except the data scientists who created them, and that are changing in weird ways because collection procedures change over time, right? And so instead you just want to
I see. So really,
do you buy?
They're interested in instead to answer causal questions, right? You run experiments, or you look for natural experiments.
Yeah.
Also, first
you look for exchangeability or hierarchy that you can create, right? Rather than attempting to look for some write down some really detailed structured causal model in your of the.
Do you think that stuff is unknowable, Eli? Like, do you think that with enough resources you could deploy social scientists to go interview drivers and collect enough data and analyze the data in interesting ways with enough time to actually figure out why different interventions were leading to different outcomes?
I guess I would argue that it's a different, that there are different ways of there are different ways of having a causal understanding of the world, right? And you know, we as individuals or you know, like, I guess now that I, you know, now that I work on biology, although I'm not nearly as experienced as Jeremy, I have, you know, I'm much more sympathetic to the like attempting to write down a causal model. But if you're a big tech company, there are no latent variables. Everything is observed. Experiments are cheap or free, right? And so the way that you know, the way that Facebook or Uber understands the you know, the world that they're operating in a causal sense is that they can do any experiment they want to answer any, you know, any causal question of interest to a particular business problem.
I don't know if that was
I think
true.
that's a perfectly valid way of you know, that's causally sufficient in the sense that you know, they can know everything they need to know, you know, about the world.
So I think a super important question that we're coming up on the edge of is, what kinds of causal questions do we want to answer and for who, right? I am not, you know, I'm not interested in developing methodology to help large tech companies get more ad revenue, right?
Well, me neither.
Right.
That's why I do biology now.
Right. And I, you know, one of the reasons
drug companies get more revenue.
Yeah. It's a little murkier, I guess. Well, so, I mean, I think one of the reasons that we have such a fragmented literature is that we have so many different people trying to solve so many different questions, where some of them know the model and some of them don't. And I mean, a part of what will help us organize this reading group is, I think, getting some consensus on the category of question we want to answer.
One thing which is kind of interesting to me is multi-scale causal inquiries. In fact, I think we chatted about this in the past when you were describing your interest in sort of networks and how networks sort of work. But one thing which seems true about a lot of systems is that you can have causal knowledge at certain levels, but maybe at another level, you don't have complete causal knowledge, but it needs to be consistent between levels in some sense. So like, you know, if you're thinking about modeling a gas, for example, right, and you're thinking about interventions on temperature. Well, of course, at the level that you're thinking about interventions on temperature, you may not be thinking about the molecular level, right? But models at the molecular level have to be consistent in some sense with, you know, the P V equals nRT level, right? Where you're just thinking of it as an ideal gas. And I've been interested in a while about this sort of thing. I don't know much about it, but it seems like an important dimension to consider in modeling, because it's sort of like if you move between levels and you don't have a mechanistic description or a causal description at one level, it has to be consistent in some way with another level, with the other level. But how that works is, you know, kind of ambiguous.
This is related, I think, to a whole other PPL area, which is how do we write probabilistic programming languages that are good at thinking about couplings of distributions, which has lots of applications beyond what you're talking about. But one application is two distributions that you want to couple at different levels.
Right.
I have to jump off, guys, but I left that forum there
also
if you want to.
Thanks. Yeah, this one works. Thanks, Robert. Yeah, thanks everyone, and have a happy holidays, happy break.
Yeah, have a happy Christmas.
Have a good break. See ya.
Christmas, happy Hanukkah in the past.
Yeah.